is the point of doing this thing? Like, why do we care about the three-sided dice? And I want to put it on our little nice little collection of random variables. I think I drew a little picture of this last class, or a few classes ago. But now let me draw another new picture. Now that we've have a few other ones, and I kind of think of this as like a little zoo. Is this a zoo of random variables? I always tell people who visit Guelph that the Arboretum is a zoo for trees. And in this class, you learn about a zoo of random variables. This is one of the things we sort of did towards the end of the course. Oh, okay. And maybe move this up here. Maybe this move. Go up there. Okay. So I have the zoo of random variables. These are all the different named random variables we learned. And I think we have two based on coin flips. So based on coin flips, when we look at a coin flip category of our zoo. And there were two based on coin flips. There was the binomial, and this depended on n and p, and it has these nice looking bar charts like this. And then there was also the geometric. That only depends on p. Okay, and the binomial, the geometric is this one that it goes down, 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 and it starts either at 0 or at 1, whereas the binomial is centered somewhere around its mean, which is n times p. So this is what I mean when I say a zoo of random variables. These are like the named random variables that we found so far. And we did the binomial and the geometric. And then the last few classes, we had their limits, the limits of coin flips, And so that can be another section of our zoo. And the two limits of coin flips, I would say, there was the normal or the Gaussian distribution. I always like to call it the Gaussian distribution because I don't like to make people feel abnormal because they're not Gaussian. And that had two parameters, mu and sigma squared, the mean and the variance. And this was a nice continuous one that looks like this. Let me draw it not centered. So again, it's centered around the mean. It's nice like bell curve with inflection points at mu plus sigma and mu minus sigma. Okay, and then we also talked about how we get this limit. So the binomial becomes the Gaussian in the limit that, okay, you have to rescale. We did this. I'm trying to think of what we actually told you on how much detail we went into. Okay, the number of coin flips has to go to infinity, I think we said. And then we said you can approximate it by its mean. So the binomial and p is approximately the Gaussian, the normal, with parameters np and n times p times 1 minus p. I think that's the way we said it. Okay, this is the Gaussian distribution, also known as Mr. Normal, big script n. Okay, I think that's what we said. That was one approximation. And then the last few classes, we did two other approximations. I have to expand my zoo over here, because there was one other limit of coin flips. There's actually another limit you could get, and that was the Poisson. Let's do this in red, the Poisson. And that only had one parameter called lambda. And the Poisson looks like this. Okay, it's got bars again, but the bars are a little bit different than the bars from the binomial. And the binomial converges to the Poisson as well in a different limit when n goes to infinity and at the same time p goes to 0. So if n times p is big, then n is going to infinity and you have the Gaussian. And then if it's p is going to 0 at the same rate as n is going to infinity, and you have lambda equals n times p is fixed. So the product of n times p is fixed even though n is going to infinity and p is going to 0. Then you have this convergence to this Poisson random variable. Okay, and that was what we did a few classes ago. And then last class, we did one more limit, and that was the same limit. The n goes to infinity, p goes to 0 limit. And that was for the geometric, though. So if you do the limit of the geometric, then we got the exponential. And this is like how long between beeps on our little machine. The exponential also with rate lambda. And we only calculated the cumulative distribution function last class, but it turns out the probability density function also looks like this. The PDF is also some kind of smooth going down where it's just like the geometric. These are the ones we've done so far. Oh, there's one more we actually did that is kind of in its own category, and that is the dice roll distributions. Dice roll distributions. Let's add another box here for dice rolls. Let's put the box down here. dice rolls. And we did, very specifically, we did one dice roll. We did an n-sided dice. This is what was called the discrete uniform. And that is an n-sided dice. N-sided dice. And the nice thing about the n-sided dice is it has a very nice probability mass function. The distribution is completely flat. They're all equal. Okay, I did a bad job drawing it. Let me try again. They're supposed to be completely flat. I guess if you want to draw a completely flat line, you start by drawing the line, and then you divide it up like that, right? So it's equally likely to be 1 or 2 or 3 or 4 or 5 or 6 or whatever. And that converged to the uniform distributed, the continuous uniform. Sometimes called U. That's not a U. Let's try U again. U. And I think the way we were doing it was the U on 0, 1, and that is a continuous random variable whose probability density function is a rectangle. Okay. These are all the named random variables we saw so far in the course. Of course, before we did any of these, we talked about how random variables can be anything. And you should really think of these are special ones that come up more often than other ones. But random variables can be anything. It's not that these are the only ones. Of course, anybody can make up a weirdo random variable, and it could be super interesting. So don't think that these are the only ones in the world. These are just some cool examples that we put in our zoo so we can go look at. These are all the ones we've done before. This is a good time to pause. Are there any questions or comments? Maybe I missed one. Is anybody else? Is there one missing from the zoo? Did we get them all? Questions or comments about anything in the zoo? So the thing I'd like to do today is we're going to expand the zoo by 1 by combining the dice rolls with the binomial. Because if you remember, the binomial, it's actually about coin flips. It's adding up coin flips. It's how many coin flips. The binomial is really a sum of coin flips. So this is a sum of coin flips. Was the binomial, okay? A sum of coin flips. And now I want to ask the same question. What about a sum of dice rolls? Where would that be? And that's like a missing spot in our zoo. Okay, you see? Where is a sum of coin flips? We have in our zoo a sum of dice rolls. Where is that? We did one dice roll. That's missing from our zoo. You see, there should be something there. We did the sum of coin flips. We did dice rolls. What about the sum of the dice rolls? Where is that? How do we get that one? Okay. Is this one nice? Or is this some like weirdo distribution that doesn't deserve to be in our zoo? That's what we're going to answer today. Okay? And to do it properly, I have, as you saw on the mathematized question, I have the so-called infamous 3-sided dice. Here's the infamous 3-sided dice. It's in my hand. And now I'm questioning, did I already show you guys the infamous 3-sided dice? I don't think I did. All right, here's the infamous 3-sided dice. Get ready. It's going to blow your mind. How could you make a dice with 3 sides? How does that work? Wouldn't it fall over? How on earth could we do it? Here it is. The infamous 3-sided dice. There's 1. There's 2. There's 3. 3-sided dice. Wait a second. They put 1 on here twice. Hey, this is just a 6-sided dice that they labeled differently. I feel ripped off. In all actuality, these are quite expensive. I don't recommend buying a lot of 3-sided dice. So for the question today, where I said I'm going to roll 24 3-sided dice, I'm going to cheat and I'm going to roll 24 6-sided dice. Okay? And then we're just going to pretend that 4 is 1 and 5 is 2 and 6 is 3. So we're sort of simulating the 3-sided dice, the proper 3-sided dice, by using a 6-sided dice. So that's nice. And then we're going to see the answer that we're going to get to. It will work not just for 3-sided dice, but it will work for any sort of dice, mostly. Okay, well, so we'll get to that. But the question we want to ask, and this is what we're going to try to do at the end of the class. By the end of the class, we're going to roll all these dice. I'm going to take all of them. We're going to roll them, and we're going to try to predict what is the total. What is the total of all these dice? And of course, we're not going to be able to get it right exactly, but we want to have a good understanding when I roll these 24 dice, what is the sum going to be approximately? Okay? And to help us with that, I have us starting by calculating the mean and the standard deviation. And we'll see that this is a good starting point for the guess. Okay? The mean and the standard deviation. So that's why we're starting with this. We're going to do this calculation. We're going to turn this calculation into a prediction, and then we're going to roll the dice and see, did we get it right? Okay? Now, doing the mean and the standard deviation, there's the hard way and there's the easy way to do it. The hard way to do it is to try to figure out the full distribution, right? Figure out the probability that the sum is 7, figure out the probability that the sum is 8, and then do the full sum, 7 times this probability, 8 times this probability, add them all up. That will take you all day because doing the probabilities is hard, and then doing the sum of the probabilities times the value, that's also hard. So sometimes when you do the mean, the average, you want to figure out the actual probabilities, and sometimes you want to use a trick. And in this situation, you absolutely want to use a trick. I'm not going to calculate the probability that the sum of 24 dice is equal to any particular number. I'm going to use a super simple trick that calculates the mean of the sum without having to calculate the individual probabilities. Now, 40 people almost have answered. So either many people do not know and have no idea, or you guys all know the trick already. Does someone know what is the trick to calculate the mean? Yeah. Yes, exactly right. So the mean of the sum is related to the mean of one single dice roll. So if you know the mean of one single dice roll, to get the mean of the sum, you would add up the mean of all the individual things. In this case, there's 24 copies of the same thing over and over again, so you multiply it by 24. So that's what we're going to do. We're going to get the mean of the sum. In fact, let me do that before I even reveal the answer. So we're going to do 24. Okay, let's go back. 24 three-sided dice. And the mean of the sum, it's always, if you're doing something n times and the individual probabilities are some average, you just multiply. Let me write this. The average of any individual dice roll, I'll say it like this. The average of x1 plus dot 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 plus xn is equal to n times the individual average. Some people will write this as n times mu if they were told x has mean mu, and let's say it has some variance, sigma squared. So the individual dice rolls have some mean and variance, and you can find the mean of the sum by multiplying. And we saw that before, that you can add up the individual expected values. Expected values are so-called linear. If you're taking linear algebra class, you will appreciate this word, linear. They respect sums. That's another nice way to say it. They respect sums. E is linear, E respects sums. Okay, very nice. That's the mean of the sum. That one would be n times mu. What is mu? Well, we have to figure it out. What is the average of one individual dice roll? That one I can do, and it's not too bad, because a dice roll is either 1 or 2 or 3, and they're each with probability 1/3. Okay, so what is the average? It is 1 times a third plus 2 times a third plus 3 times a third, which is also known as 2. Okay, very nice. You roll a 3-sided dice, on average, you get 2. So the total will be 2 times the number of dice, so will be 24. So the mean of the sum, let's call the sum S. Let's call that S. S for sum. The expected value of S will be 24 times 2, which is 48. Okay, beautiful, 48. Let's see how many people got 48. 48. Okay, so some people didn't know, but 48 was a very common answer that over half the class got. Very good, that's wonderful. That's the mean. Again, there's a hard way, there's an easy way. Sometimes you gotta use the formula from the hard way. That's the only way to do it in some problems. But sometimes you gotta do this one. In probability, there's often many ways to do a problem, and you gotta make sure you know all the ways so you can pick the easiest one. Same goes with the standard deviation. This one, I think, is a lot trickier. I think we did mention the rule. The trick to get the mean and the trick to get the standard deviation are a little bit related, but let's see how many people remembered it. Okay, so this one is split all over the place. The most common category is the does not exist, and there's no majority on any single answer. There's things all over the place. So this one, I will have a revote, and we'll do it, but let's try to brainstorm what is the trick for the standard deviation. We talked about the trick for the mean. Trick for the mean. The mean. The trick for the mean was that averages add. Right? So instead of figuring out what's going on, you can just add up all the averages. What is the trick for the standard deviation? Actually, let me write the trick for the variance. Because the trick for the standard deviation is first you figure out the variance, then you convert it to a standard deviation. What is the trick for the variance? Now that it's written like this, does anyone remember what the trick is? Yeah. This is very good. So you are remembering what you have told me is the classical definition of the variance. So you are remembering the definition of the variance, which is wonderful. And in some problems, you absolutely need to know this, and it is super important. The variance is x minus its mean all squared. And this is the variance. Oh, actually, let's do an example of this. Let's do this for one individual dice roll. So we need to find the variance of the sum, but why don't we apply this formula to find the variance of one individual dice roll? In our case, the variance of one dice roll, it's the average of x minus 2 all squared. And that's because we figured out the average was 2. What is x minus 2? Well, x was either 1 or 2 or 3. So x minus 2 is either negative 1 or 0 or 1. And this is with probability 1/3. This is with probability 1/3. And this is with probability 1/3. Okay, so if somebody says, I'm thinking of a random variable, it's negative 1 or 0 or 1, each with probability 1/3, please find the average value of that thing squared. Well, I would just square up the things and multiply by the probabilities. So minus 1 squared times a third, plus 0 squared times a third, plus 1 squared times a third. Okay, and if I add this up, negative 1 squared is 1, so I got a third here and a third there. That is 2/3. 2/3. So the variance of any individual dice roll is 2/3, and that is very good. That came straight from the definition. I think this is the only way to do that part. The trick I wanted, though, was how do I get the variance of the sum? You see, because the sum is some crazy complicated distribution. Oh my God, we got to add up 24 things. We're going to be here all day. The sum can be extremely complicated, and if you try to calculate the exact distribution of the sum, it is a hard time. So you want to find a trick to find the variance of the sum without calculating the whole distribution. And so we can't use this formula, because this formula relies on knowing the individual probabilities. We don't know the individual probabilities for the sum. That's what we want to avoid. So what is the trick for the variances? Yeah? Yes, okay. So basically you're saying, for the variance, I actually did it the exact same way as the mean. You just multiply. If you replace expected value here with variance, you can still multiply, and then it all works. And then to get the standard deviation at the end, you just took the square root. And the way I would summarize this is, the trick for the mean is that averages add, and the trick for the variance is that variances add. Variances add. And I will add a little important star, and the star is only if independent. Only if independent. So averages always add, but variances add for independent things. And this is something we talked about way back when we did variance. Why is it that the variance of the sum of two things, if the two things are independent, then the variances add together? And in this case, we're rolling a bunch of dice. What happens on one dice does not change the probabilities on another dice, so the variances will all add together. And if the variances all add together, I can get the variance of the sum. The variance of S is the variance of x1 plus dot 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 plus x24. And there's 24 copies of the same thing. You could write this as the variance of x1 plus dot 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 plus the variance of x24, adding all the variances together. But it's 24 copies of the same thing. We have a name for that. It's called multiplication, the variance of any individual dice roll. And fortunately, we've done the variance of any individual dice roll. It is 24 times 2/3. And look at that. The numbers work out nicely. 24 divided by 3 is 8. So 8 times 2 is 16. 16. So the correct answer is 16. That's what we're looking for. How many people said 16 in the mathematize? How many people said 16? Nobody said 16. Funnily enough, 16 different people said 4. But nobody said 16. And that's because I made the second classical blunder that everyone makes all the time, which is I mixed up standard deviation and variance. The question is asking for the standard deviation. I calculated the variance. You need to do one last step at the end, which is to take the square root. So the standard deviation, the standard is the square root of the variance which is the square root of 16, which is 4. Look at that. It worked out to a nice round number. Very nice. That means whoever made the problem is a true genius. Okay, when the numbers work out nicely. In real life, they often don't work out nicely. You might see this.
Professor Nika.
Oh, no. Yes, okay. Please, go ahead.
So you did n times the expected value of x and n times the variance of x because all of the x's had the same distribution.
Yeah.
But your basic point was that the expected value of the sum
Yes.
was the sum of the expected values.
Yes.
And that was always true.
That's always true, yes.
And
it's
the
an amazing fact.
variance of the sum was the sum of the variances, but only if the random variables were independent of one another.
I shouldn't say only if. I should say if they're independent, then it works.
Okay.
It might work in other situations too. In fact, I believe the rule that you need is something called uncorrelated.
Okay.
So works if and only if. This is a good thing to get right, is the direction of the implications works if and only if the x's are uncorrelated. If they're not uncorrelated, you have to add on a term. You might be familiar with the cosine rule from like grade 12 geometry. So the Pythagorean theorem says that you can add, to get the diagonal, you can add the two sides if it's perpendicular. If it's not perpendicular, you need to add some extra correction term. And the rule for variances is actually mathematically exactly the same as the Pythagorean rule. So it works if the things are uncorrelated. That means they're like at 90 degrees to each other in some sense. They don't affect each other in some particular sense. And if they are correlated, you have to add on a correction term. We will save the correction term for math stat in third year.
So let's set up a trickier question. More challenging question. What if you rolled a 3-sided die a certain number of times and you rolled a 4-sided or a 5-sided?
Oh, you want to make
die,
it, you want to say, instead of having only 3-sided dice, what if I had a collection of a hodgepodge collection of dice and I rolled them all?
Absolutely.
I think what you're pointing out is you could still do the problem exactly like we did it before. The only step that would be different is instead of doing 24 times one number, you would have to add up the numbers individually. But other than that, everything we've done would be exactly the same.
Exactly.
Yes, that's right. What we're going to do is actually going to let us do
a tougher problem.
Any collection. Yes, well, maybe we'll get to a tougher problem in a second. Yeah. This is a good point.
Because you have so many different dice.
I do. Well, yeah, I only brought the 6-sided. Well, no, that's a lie. I thought I only brought the 6-sided ones, but I brought a whole bunch of other ones too by accident. Okay, we're going to stick to the 3-sided first. Get this one nailed down, and then we'll do that at the end. We'll do the extra big dice and try to predict them. Okay, but the main technical thing we had to do is now done, is calculating the mean and the variance. This is such a bread and butter skill. I can almost guarantee you're going to have to do something like this on the exam. So it's a good place for questions. Are there questions about the mean and the variance? Okay, so now the question is, how do we use the mean and the variance to predict how to use the mean and the variance to predict the value? How to use the mean and variance to predict values. Okay, and going all the way back to what I actually want to talk about today is where does this fit into our zoo? Is, there should be some kind of distribution that's like the binomial. I guess it would be the binomial is called binomial. It's a binary options. The coin flip is either heads or tails. This is the trinomial distribution, which is something like the sum of 3-sided dice where there's 3 things. So this distribution would be the trinomial distribution, and it would have some like really wonky, weird formula, and it would again have some kind of funny shape histogram. And we would like to calculate the probabilities without doing all this stuff, without doing this. So we would like to avoid the exact and just get a nice approximation. Okay? And the hint on what to do is already in our zoo. If you understood the zoo of random variables we've done so far, we're basically adding on one thing. And when we had the binomial, a lot of times we calculated exactly with the binomial. But sometimes, when it got annoying, what did we do? We just replaced the binomial with the Gaussian. And replacing the binomial with the Gaussian says just calculate the mean and the variance, and then put those in as the distribution. And that is exactly what we're going to do here. So here is the fact this is one of the coolest facts in the whole universe, and might legitimately be up there for my favorite theorem, is it works not just for the sum of dice rolls, but the sum of any random variable. All right, we're back. So the sum of any random variable, we're going to put any star because there are technically some terms and conditions. And in general, the distribution itself is nasty. But the thing that is true, and the amazing thing that absolutely should go in our zoo, is the sum of any random variables. The actual distribution is not worth looking at. But the arrow connecting the sum of any random variables to the Gaussian, that is a beautiful thing. Let's do this one. We should pick a special color. Do I have a special color? Ooh, do I have like rainbow or something? All right, let's pick we have a nice pink color. We haven't done that yet. Okay, this is a beautiful thing, and it's just like the arrow from the binomial to the Gaussian. That arrow works for any sum of random variables. And this sum has a name. We're going to move the label for the dice rolls somewhere else. This is called the central limit theorem. And this is one of the big results in probability. And I think this is like the reason that probability is nice, is like things that are very complicated, sometimes by some kind of like weird cosmic miracle, you can calculate them using things that are simple. And the central limit theorem just says a sum, let's put it in quotes, a sum of random variables, of independent, they have to be independent, like they are here, independent random variables, is well approximated. Yes, this is the thunder of the gods getting excited by the central limit theorem, is well approximated by a Gaussian. So in other words, even though it would be very, very hard to get the exact distribution for the sum of dice, we can approximate it by the central limit theorem and say it's approximately a Gaussian. And so a good example is we can say, so we just use the CLT, the central limit theorem, to approximate. And so, for example, I could find the probability that S is between 52 and 44. What's the probability S is between 52 and 44, where S is the sum of these three-sided dice. And by doing our normalization trick we learned about in the central limit theorem, or in the Gaussian distribution days, so I subtract 48 and I divide by 4 everywhere. This is the probability. 44 minus 48 is negative 1 when you divide by 4. The S minus 48 divided by 4, this is a random variable minus its mean divided by its variance. And that is kind of standardizing the random variable. By the central limit theorem, this is approximately a standard normal, which we called Z or Z. So this is going to be approximately the probability that a standard normal is between negative 1 and 1. This is one of those famous ones that is 68 point something %. This is that now we have to give Professor Humphrey the microphone again so he can tell us the more decimals.
68.26%.
26 are the next two decimals. Okay, great. 0.26 percent. This is a really famous one that if you work with these kinds of things, 1 standard deviation, 2 standard deviations, 3 standard deviations, you'll sort of memorize over time. So 68.26%. So what I'm saying is if we roll all these dice, we should get a number between 44 and 52 about 70% of the time. That's pretty good. You could go one more standard deviation. That'd be between 40 and 60. That would be like 95% of the time. A lot of people summarize this, and they will say something like, S is 48 plus minus 4. And this is often shorthand for meaning the mean is 48, the standard deviation is 4, and if you wanted to know probabilities, you could sort of approximately calculate them with this central limit theorem. So between 44 and 52 is going to be 68% of the time, and between 40 and 56 should be like 95% of the time. That's 2 standard deviations. Okay, and now is the exciting part. We get to see, does it actually work? Let's roll the dice and see, is it between these numbers? Like, are we close? maybe this is kind of underwhelming, but I think this is so cool that it's like something you can't calculate, but you can still find the answer. You sort of skip all the hard work. It feels like you're doing magic. Okay, questions or comments about this before I roll the dice, or as I roll the dice?
Might be worth pointing out that 3 standard deviations takes you to about 99.7%.
Okay, yeah, that's very good.
Very little is in the tail.
Yes, that's right. So like the probability of if the sum is like less than 36, then we can eat our hats. Yes. Okay, there's a question back here, yeah. Yeah. The sum of any random variable. So it doesn't have to be a dice roll. It could be any weirdo distribution. So someone on the street is like, I have this like crazy dice. As long as you're adding up the same thing over and over again, the central limit theorem will apply, and you can approximate the sum by a Gaussian. Yeah, so sums of one thing repeated over and over again are approximately Gaussian. That is the central limit theorem. Yeah, very good clarification. Yeah, you need the brackets around the any sum of random variables. Yeah, okay. All right, let's roll them and see what we get. Okay, and the first thing you got to do is make sure you have the right number of dice, because if you have the wrong number of dice, it's not going to work. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I have to banish the 3-sided dice. Okay, yeah, banishing the 3-sided dice. Okay, let's zoom out a bit. You guys can help me count if I did something wrong. This one's here. Okay, so that's 6 and 6, 6 and 6. Okay, and I guess there's a lot of dice, so let's roll them in two groups so we don't get too crazy. Okay, and I'm going to collect up all the ones that are the same values. 2, 2, 2, 5, 5, 4, 4. Whoa, look at all these 2s. This is wild. 1, 4, 5. We got so many 2s and not a single 3. Oh my God. No matter. Okay, there's the 1 up there. Okay, I'm going to roll some more. Ah, look, the 3s are now appearing. 3, 5, 4, 1, 2, 6, 1, 4. Okay, and remember, we're counting 4s as 1s and 5s as 2s. So I can move these together. 5s are the 2s, and the 6s are the 1s. So this is the number of each roll that we got. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9 1s. 9 1s. So 9 times 1 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 2s. 12 times 2 plus 1, 2, 3 3s. 3 3s. So our sum, 9 times 1 plus 12 times 2 plus 3 times 3, 9 plus 24 plus 9, 18 plus 24, 42. Did I get that right? Okay, and what did I say on the board? Oh, look at this. According to us, this is a kind of a rare roll. So we got a roll that is outside 1 standard deviation, but is within 2 standard deviations. So we got sort of like 30% unlucky. This is like a bottom 30% roll over here. And actually, if you look at it, right, if you look at the distribution of the dice we got, which is why I kept them in order and didn't just add it up, you can see we got a little bit unlucky. We didn't roll many 3s at all. Normally, you should roll about a third of your rolls should be 3s. And in this case, we got quite a bit less than a third of our rolls were 3s. We should get 8 3s. We only got 3 3s. And that's why we got a little bit on the low side, but still within 2 standard deviations. And so this is the beautiful thing. We can still sort of know where these things are, even without knowing the exact distribution. And this is called the central limit theorem. This is super duper useful. You might say, why do people care about this so much? Like, how often are you rolling lots and lots of dice? It turns out this is one of the most useful approximations in all of statistics. Can anyone think of a real life situation where you would, quote, roll a lot of dice? Why do people care about this? Who cares about dice? Only me, I guess. You have to expand your mind. What could a dice roll be, right? This works for anything. They don't have to be physical dice. What could the dice roll be? Yeah. I think you're thinking the right way. The individual dice roll can actually be anything. If the individual dice roll is anything, then what is the sum? What is this operation of adding them up? So the reason this comes up all the time, a good example is a survey. Imagine an individual person is a dice. I ask you some survey questions. On a scale of 1 to 5, how much did you like the course? Okay? You tell me 5, you really liked the course, 1, you didn't like the course. One individual person might have a weirdo distribution. Maybe they have something quite weird. But if I have enough people in the course and I add up all their answers, or if I take the average of all their answers, that's adding it up, and dividing by a number, if you add up lots of individual things, it'll be the normal distribution. So if you have enough people answering a survey, the outcome of the sum or the average will follow this central limit theorem. That is why it's so important. When you collect data in science experiments, so surveys or anytime you do an experiment, you do a physics experiment, how many electrons came out of our physics machine? Okay, that's some kind of dice roll. Is it 1 or 2 or 3 or 4 or 5 or 6 or 10,000 electrons? We don't know. Some kind of weird distribution. But if we repeat the experiment enough times and we add up the results over many different trials, then we will get we will know the average is Gaussian. We can narrow in on what does that mean. So that is the reason. It's repeating experiments over and over again. The individual dice rolls, you should think of the outcome of something you care about, and doing it many times and adding it up is repeating the experiment enough times to build up a sample size where then you can be sure what is the average and what is the distribution, even if the individual distribution is unknown. So even if your machine does something wonky, the average overall will only depend on the average and the standard deviation. That's why the central limit theorem is important. Okay, let's write this down, and then we will maybe call it a day. Okay. So in real life, the dice roll equals one sample or one sample of an experiment / survey, experiment / survey, and the total, and by the way, it also works for the average. So we're not making or average equals results combined from many samples. And that is the reason this is so important, is this is kind of the workhorse of when you run a science experiment and interpret the results, you will end up using something like the central limit theorem to say, okay, we saw this thing happen. That was unlikely to be due to chance. You know, if the science works the way I think it is, we should get an answer between 44 and 52, and we did. You know, like that's the kind of thing you would say. So that's why it's important. It's not just for board games. It is used to interpret experiments / data. Okay, and that is what you would do if you continue taking stats courses. You will do more and more of this kind of stuff. Everything we've been doing has been without the data. We're talking only about dice rolls, but the data gets introduced in the next stat classes.
Professor Nico, I have something to say with my dead microphone.
Okay, yes, all right.
Okay, listen carefully because I have a soft voice. We have a class on Monday.
We have a Monday schedule.
We have a Monday schedule.
On Friday.
It's a trick. Friday, remember that Friday is Monday's schedule, Thursday is Tuesday's schedule. Keep track of that in case it might affect your other courses. I have office hours on Mondays, 3 to 4:30, so that means that I have office hours this Friday from 3 to 4:30. So I wanted to tell you that. And
there's a question in the front. We can do that as well. Yeah.
Yeah.
Oh, a random forest. Okay, yeah, I can tell you the 1 minute explanation of what a random forest is. A random tree is a method to classify something. So you could say, like, I have some data, I want to know if this is a good outcome or a bad outcome, and a random tree asks a bunch of questions. Like, does it have red hair? Does it have this? And a random forest is you take a bunch of random trees and you glue them together. We did random forest recently in my data science class. So if you keep taking this stuff, you will learn about random forest in data science. Yeah, very good.
And this class, whatever it's called in 2 days, is it a Friday, is it a Monday? It's an important one.
Well, we will finally do the difference between discrete and continuous, which we have been promising for a long time.
Galore.
And we're going to do some infinities. It'll be a fun class. Okay. All right. Let's stop there. See everybody on Friday for our Monday scheduled class.